Standard construction is an additive process. Whether you are stacking blocks of limestone or laying bricks, the method allows for a clear margin of safety. You can test the weight as you go, and if a stone is misaligned, you can simply remove it and try again. But the Kailasa Temple in India represents a radical rejection of that logic. Instead of building upward, engineers chose a subtractive path, slicing straight down into a solid basalt plateau to carve an entire multi-story complex out of a single piece of the Earth's crust. This top-down method introduces a physical constraint that modern engineering rarely encounters. When you are carving a building out of a mountain, there is no margin for error. You cannot put the earth back once it is removed. A single misplaced hammer strike or a deep structural crack would instantly ruin the entire monolithic temple, rendering years of work useless. This forces us to look closer at the physical evidence. If these early cultures were truly primitive, how did they execute a zero-error logistical path that modern crews struggle to replicate today? In Iran, the tombs of Naqsh-e-Rostam sit high within the cliffside of the Zagros Mountains. Mainstream explanations suggest workers carved these massive facades while dangling from long hemp ropes. From a physics standpoint, that explanation is difficult to sustain. A suspended worker lacks leverage. The force of a heavy hammer swing simply pushes them away from the rock face. Delivering the thousands of high-impact strikes required to hollow out a mountain requires a level of stability that a rope cannot provide. We see a similar geometric hurdle in Ethiopia, where architects under King Lalibela excavated 11 cathedrals straight down into dense volcanic bedrock. To avoid a catastrophic collapse, every arched window and vaulted ceiling had to be mathematically mapped out in the dirt before the first piece of stone was ever removed. Achieving flawless 90-degree inner corners within a solid mountain suggests the use of geometric tooling that is far more sophisticated than the primitive labels we often assign to this era. Once the carving begins, subtractive engineering creates a massive logistical problem. What do you do with the waste? This is the rock ship of Masuda in Japan, a granite monolith featuring deep, perfectly symmetrical indentations. Shaping a 500-ton block like this should leave behind thousands of pounds of stone chips and debris. Yet the area around the monolith is completely clean, with no physical trace of the carving process ever being found. The Long Yu caves in China present an even more confusing anomaly. These are massive, pitch-black underground chambers carved directly into siltstone. If an ancient workforce used traditional oil lamps or torches to see, the ceilings would be coated in layers of soot. But the rock surfaces in these caves are pristine, showing no carbon residue from primitive lighting. The total absence of carving debris and torch soot suggests that the logistical reality of these sites was far more complex than the use of simple iron tools and wood torches. Perhaps the most rigorous test of ancient engineering is subterranean fluid dynamics, the ability to move water through solid rock while working in total darkness. In the dry canyon of Petra, the Navatans managed a massive subsurface network, laying miles of pipes along the cliff faces while maintaining a precise downward gradient. The math is unforgiving. If the channel angle was too steep, water pressure would burst the ceramic joints. If too shallow, the water would stagnate. To maintain a steady flow over miles of desert, they hit a mathematical sweet spot of exactly 4 degrees. Achieving this alignment through manual excavation in dark tunnels indicates a highly refined system of surveying. Deep within the jungle, the Maya city of Palenque utilizes these same principles within its own utility grid. Here, architects carved bedrock channels that deliberately taper inward as they move downhill. By squeezing the volume of rushing water into a tighter space, they generated enough hydraulic pressure to power indoor plumbing. While pressurized water is often described as a much later European invention, these underground machines prove that isolated jungle engineers had mastered fluid dynamics centuries earlier. When we look at these sites together, the gradients in Italy, the missing waste in Japan, and the pressurized channels in Mexico, a global pattern of high-precision engineering emerges. Categorizing these builders as primitive ignores the mechanical genius required to execute these zero-margin projects. Consider the Aussie Rayon in Egypt. The erosion patterns on these submerged granite pillars suggest the structure was exposed to prolonged, heavy rainfall, conditions that haven't existed in this region since long before recorded history. Sophistication in the ancient world is measured by the flawless mathematical manipulation of the raw earth. Our history may not be a simple ladder we climbed upward. It looks more like a series of profound excavations, and the deepest layers suggest a level of mechanical mastery that we are only just beginning to understand.